Alright, in this video we're going to do section 2-3, analyzing the graphs of functions. And what we're going to learn in this section is using the vertical line test, finding the zeros of functions. Remember, those are just where we cross the x-axis. Determine intervals on which the functions are increasing or decreasing, and determine relative maximum and relative minimum values of function. Those are just sort of like the peaks and the valleys of the graph. We'll determine the average rate of change for a function. And we'll look into even and odd functions. I think that's at the very end. Alrighty. In the previous section 2.2, you studied functions from an algebraic point of view. In this section, we're going to study functions from a graphical perspective. So the graph of function f is the collection of ordered pairs x comma y, or remember with our function notation, f of x is equal to y. We put an x value into the function, we run it through the function, and out pops the y coordinate. So the x comma y we can also write as x comma f of x, such that x is in the domain of the function f. As you study this section, remember that x is the directed distance from the y-axis, and y, or f of x, is the directed distance from the x-axis. Like here, if we have this point, and it looks like this point, we'll call it 1.3 comma 2, just to give it a number. The x-coordinate is how far you are away from the y-axis. So this x-coordinate of 1.3 means we're that far away from the y-axis. And y, or f of x, the second part of the ordered pair, is our directed distance from the x-axis. So here our y value is 2. That means it's a distance of 2 to the x-axis. And it says directed distance, that could be positive or negative. Alright. Example 1. Use the graph of the function f as shown in the figure to find these three things. A, the domain. B, the function values, f of -1 and f of 2. And C, the range of f. Let's see here. First, they want the domain. And remember, the domain is just what x values can we plug into the function. Well, if we look way over here, the function's not defined. It looks like the function starts right here, so that's where the domain starts on the x-axis. And that would begin at -1. And then our function goes up, down, always moving to the right, and then it stops right here. And that looks like it's above the point 5. There's our coordinate 5 comma 2. And notice too that on the left-hand side where the function starts, we have a colored in circle. And over here on the right where it ends, we have an open circle. So to find the domain, those are just all the x values that sandwich in x. So we start here at -1. The function goes along to 5. And then we have less than signs. There might be an or equal to under them, depending on the dot. And here on the left-hand side, it's above the -1, we have the colored in dot, so that'll be less than or equal to. The other endpoint is an open dot, so we'll just leave that as strictly less to. Those are all the x values in between that we plug into the function to get the y values, that give us our ordered pairs to graph the function. Letter B, some function values. It says f of -1. So we're looking at an x value of -1 and seeing where the function is defined, if it is. So here at x is -1, we can look down and the function's not there. But when we look up, we see the function is there and we hit that colored in dot. So f of -1 is equal to 1. And then that's this ordered pair, -1 comma 1. Number f2, we're also looking for part B, f of 2. So we go to our next value of 2, we look up, the function's not there, but if we look down, there it is. And we hit it and look over to the y-axis, that's at a height of -3. So f of 2 is equal to -3. The last thing they asked for, part C, the range of f. Remember, the range are the y values that come out of the function. So if you look at the function, the highest it ever goes is right up here. And the lowest it ever goes, the lowest of the valleys, is down here. On the y-axis, what does that values run from? And that would go between -3 and +3. So for the range, we could write bracket -3, 3. And remember, the brackets mean that those endpoints are included because we do have, those are colored in dots there. So we can get all that information just by looking at the graph. Vertical line test. I know you've heard of this before. A set of points in the coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than one point. So in example 2, we're going to use the vertical line test to decide whether the graphs represent y as a function of x. And you notice as we start moving this line along here, just about any point, we're hitting the parabola twice. This parabola is opening to the right. This red line is hitting that parabola always at 2 points, so this is not a function. We move on to letter B. Here we're only hitting the graph at 1 point. As we slide across, we're only ever going to hit that function at 1 point. So yes, this is a function. Last one. We're going along. We're moving along here, and we're hitting this downward sloping line at just 1 point. 1 point, we're fine, and then we hit this open spot. There is no graph there at all. So are we still passing the vertical line test or not? Back up to the definition. If and only if no vertical line intersects at more than 1 point. Here we're intersecting at 1 point, here at 1 point, here at no points. And that is not more than 1. So even if there's a gap in the graph, yes, that can be a function. Zeros. If the graph of a function of x has an x-intercept at a comma 0, then a is a 0 of the function. Or again, zeros are just where the function crosses the x-axis, if it does at all. So the zeros of a function of function f of x are the x values for which f of x is equal to 0, or our y value is 0, or again, that's where we cross the x-axis. So find the zeros of these functions. For letter A, we have 3x squared plus x minus 10 is equal to 0. And let's see, can we factor this without the quadratic or completing the square? 3 is a prime number, so it's got to be 3x and x. Factors of 10, 5, and 2. I'll multiply my 2 by the 3x and put my 5 here, and that should get us to the plus 1, because it's, what would that be? Minus and plus. And let's just check here and see if that does work. Outer terms 6x, inner terms minus 5x. 6 minus 5 is 1x. So that is our factorization. And then we would set each of those factors separately equal to 0. When we set the first factor equal to 0, we would add 5 to each side and then divide by 3. 5 divided by 3. Here we would just subtract 2 from each side. X is negative 2. Again, those are the zeros, or where this graph would cross the x-axis. And it is a squared term. It's a parabola opening up. So it does make sense that we're going to have a couple of intercepts there. Letter B, square root function. We have 10 minus x squared all square rooted, and we're trying to find the zeros, so we set it equal to 0. So how do we get rid of the radical? We square both sides. The square and square root cancel out, and we have 10 minus x squared equals 0 squared is 0. And then I'm going to add x squared to each side. 10 equals x squared. And then extract the roots. Square root each side. And we have x equals either positive or negative square root of 10. So we did a regular polynomial and then radical, and now we have a rational expression for part C. H of t is 2t minus 3, all divided by t plus 5. And we want to set this whole function equal to 0. How do we get rid of a denominator? We multiply both sides by that denominator. So here they'll cancel, and we just have 2t minus 3 is equal to 0 times anything is 0. So basically what you're going to do is just set the numerator itself equal to 0, because that's where a function will zero out. So here we're going to add 3 to both sides. 2t equals 3, divide by 2, t is 3/2. Now increasing and decreasing functions. The more you know about the graph of a function, the more you know about the function itself. Consider the graph shown here in the figure. As you move from left to right, just like we read, the graph falls from x values -2 to 0. So up from -2 to 0, this function is going downhill. It's decreasing. It is constant from x values 0 to 2. So from x values 0 to 2, we flatten out, and we're a horizontal line. And then it's increasing or rising from x values 2 to 4. Now we're going back up. You know, those are very interesting parts of a graph to know about. Where does it decrease? Where is it constant? Where is it increasing? So, and here's a more technical mathematical way to say it. A function f is increasing on an interval if for any x1 and x2s in the interval, x1 being less than x2 implies f of x1 is less than f of x2. That's just another way of saying if we pick a couple of points here, and we pick the y values that go with them, you know, above this one here would be this point, above here. You know, as we go farther negative, these are going higher and higher. Or as we get closer to the y-axis, our f of x values, our y coordinates, are going downhill. They're decreasing. The function is decreasing. A function is decreasing if for any values x1 and x2 on the interval x1 less than x2 implies that f of x1 is greater than f of x2. And it's constant if those output values are the same. F of x sub 1 is equal to f of x sub 2. Again, we're talking more about the graphs than anything else, and it's very easily to see visual if the function is decreasing, or it's increasing, or if you're at a flat spot, if it's constant. So here it says use the graphs to describe the increasing and decreasing behavior of each. So let's see here, first graph. Here, as we start where the graph we can originally start to see it, it looks like we're increasing. We're going uphill, 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 uphill. It looks like we start to flatten out, and then we're going back uphill, uphill, uphill. So it looks like here for letter A, this is always increasing. It's increasing everywhere. All right, let's look at the next one, letter B, and you know where we change from increasing to decreasing. Those are like the peaks and the valleys, the top of the hills and the bottom of the valleys. So let's find those first. Here we have a top of a hill. Here we have the bottom of a valley, and you know on those bottoms of the valleys we switch from decreasing to increasing. At the top of a hill we switch from increasing to decreasing. So let's find these intervals. Well, the function goes down off the graph here, so let's say that goes from -infinity to an x value of 1. From -infinity to 1, we are increasing. And then from the top of that hill to the bottom of the valley, that's where the function's going downhill. And those x values are from -1 to +1. From -1 to +1, the function is decreasing. And then from the bottom of this valley, we pick back up, and it looks like we head off toward infinity there. So from 1 to +infinity, the function goes back to increasing. Letter C. The graph isn't as curvy. It's made up of more straight lines with some bends in them. We can do the same thing. Here, it looks like we switch from increasing to flat. So this is an interesting point. And then we're flat for a while, and then we go to decreasing. So this is another interesting point. And let's see, you know, here's our function, which really isn't relevant very much, but let's figure out where we're increasing and decreasing. So it looks like from -infinity, way off the graph, to an x value of 0, we are increasing. And then from an x value from 0 to 2, we're flat or constant. 0 to 2, constant. And then from that x value of 2 off to infinity, we're decreasing. Practice time. You know, we got these three on the page. Use the graph to find the domain and the range. Use the vertical line test. Those should go pretty quick. Find the zeros algebraically. Determine the intervals, increasing or decreasing. And here it says graph the function, determine the intervals for which f of x is greater than 0. So pause the video, try the practice problems, turn it back on, and see if you got them right. Alright, the first one, it says find the domain and the range. So the domain and the range. Looking at the graph, it looks like it goes off there toward infinity, negative infinity, off this way also toward positive infinity. So the x values, where the function is defined, I can look at any value along the x-axis, and it looks like if I look up, I'm going to see the function. So the domain goes from negative infinity to positive infinity. The range is where the y values are defined. So if I'm up here, looking left or right, I'm hitting the function either way. From the bottom of this, looking up, that function is defined everywhere on the y-axis. But if I pop below the x-axis, is the function down here at all? Anywhere? No. So the range, again, where we are defined on the y-axis, is going to go from, and we don't need a parentheses because we do have a dot there, that would be bracket from 0 up to infinity. For 18 and 20, they give us the function, a cube function and a circle function. Use the vertical line test. First one, number 18, passes with flying colors, only hitting the graph at one point. Anywhere you hit on the circle, except a tangent point on the left or right, anywhere else you're going to hit the circle twice. So that is not a function. For 30, find the zeros algebraically. So we just want to set this equal to 0. And then we want to factor it. So let's see, here we can pull out an x squared. And then we're left with 9x squared minus 25. And I notice perfect squares here being subtracted. That is a difference of squares that we can factor down real nice. The square root of 9 is 3, x squared is x, square root of 25 is 5, and we'll have a sum and a difference of those terms. So we set each of those factors to 0. When x squared is 0, x is 0. When this is equal to 0, we would subtract 5 and divide by 3, so x is negative 5/3. And for the last one, we would add 5 to both sides and then divide by 3 and get positive 5/3. So there are the three zeros of that function. Okay, here we just have a nice parabola, x squared minus 4x. Determine the intervals where we increase, decrease, or are constant. And we see we got a parabola. And here for this parabola, there is only one bottom of the valley, so to speak. That vertex of the parabola. So if we start over here on the left, it looks like we're heading off toward negative infinity. Until we get to an x value of 2, the function is going downhill, decreasing. And then we start at that x value 2, and then we head off toward positive infinity. That function is increasing. The last one, determine the intervals for which we're positive, graph the function. So here, remember, we're just worried about what's under the radical. What is under the radical must always be positive. A square root, an even index root, must always be positive. So we're going to set that function greater than or equal to 0. And we could square both sides. X minus 1 greater than or equal to 0. And then we're going to add 1 to both sides. X must be greater than or equal to 1. And that will give us positive outputs for our function. It also does say graph it. So let's see here. If we remember our basic graphs, the square root function, would start at the origin and go up to the right. But we have a minus 1 under the radical, so our x values must be greater than 1. So all that's going to do is take this graph and move it out to an x value of 1. The assignment for section 2.3, page 207, 1 to 13 odd problems, and then this little list right here. Have fun.